Welcome to A2 Nuclear Physics. At AS level, you learned the basic structure of the atom. Now, we step inside the nucleus to measure its exact dimensions, calculate the immense forces holding it together, and mathematically model its decay. At the heart of this unit is Einstein's mass-energy equivalence. You will learn to treat mass as a highly concentrated form of energy. This is a high-stakes, mathematically demanding unit for Paper 4, but the questions are highly predictable.
We start by measuring the physical space the nucleus occupies. By firing high-energy electrons at nuclei, physicists found a simple relationship. The nuclear radius, r, is proportional to the cube root of the nucleon number, a. This tiny empirical formula is incredibly powerful. In your exam, you will use it to prove a surprising fact. The density of nuclear matter is constant across all elements at a staggering 10 to the 17 kilograms per cubic meter.
Next, we look at the energy binding those nucleons together. This curve is the signature idea of the entire unit. It plots binding energy per nucleon against nucleon number. The higher the curve, the more stable the nucleus. You will learn to calculate this binding energy by finding the mass defect, the missing mass when nucleons bind, and converting it to mega-electron volts. Notice the peak at iron 56. This peak dictates the fate of every atom in the universe. Because iron is the most stable, nuclei on either side of the peak want to move towards it. Heavy, unstable nuclei can split into lighter fragments. This is nuclear fission, the process that drives nuclear reactors through induced chain reactions. Conversely, incredibly light nuclei can join together to form heavier ones. This is nuclear fusion, the engine that powers the stars. For both, you will balance the nuclear equations and calculate the massive energy released. When a nucleus is inherently unstable, it will eventually decay. This process is completely spontaneous and random. We cannot predict when a single nucleus will decay, but we can perfectly model the bulk behavior of trillions of them using this exponential decay law. You will use the decay constant, lambda, and the natural logarithm to solve complex chronological problems, linking this directly to the concept of half-life to find out exactly how long a sample remains radioactive. Finally, we examine what happens when that radiation interacts with human tissue. You will evaluate the biological effects of ionizing radiation, learning to distinguish between the raw absorbed dose measured in grays and the dose equivalent measured in sieverts. This is where abstract physics meets real-world safety, requiring you to understand how different types of radiation cause cellular damage depending on where they are absorbed.
To master this unit, you need precision. Memorize the rigid mark scheme definitions for mass defect and binding energy. Practice your unit conversions until moving between atomic mass units, kilograms, and mega-electron volts is second nature. And track your significant figures carefully. Premature rounding will destroy a mass defect calculation.